since I started the thing.
Thank you, Lamech. Thank you.
No worries.
Finally,
I'm still doing
did your job.
I remember.
So yeah, once again, the quiz, it's 8 questions long. One of them is like a conceptual question, sort of. 6 of them are like you have to prove convergence or divergence using one of the tests. And then the last one is a power series question. We're going to talk about more about power series today. Monday, hopefully, we'll be able to get into Maclaurin and Taylor series. But we'll see. It depends on how today goes. But for the most part, Monday's lecture shouldn't be on the quiz, but it will be on the final. Okay, Maclaurin and Taylor series are on the final. Any questions about quiz 3? Know your tests, okay? Know your tests to know when to use each one. I hope you guys have looked at some practice problems. I hope you guys practiced some more problems during recitation yesterday. And can someone please explain why do people keep joining, like, I get notifications on recitation days that people are joining my thing instead of China's. Is it just because, like, oh, I didn't know we're meeting with China today versus we're meeting with China? Never mind. You know what? Never mind. Okay.
Oh, like on recitation, they're joining your.
Yeah. I don't know
The
why.
reason why was because.
Oh, no. Yeah, when China didn't post the link.
Yeah, so some people, I guess, clicked yours.
Yeah, so people must have clicked yours.
But it's the same link every time. So.
Okay. All right. What else? So know your tests, and then know how to find. We're going to talk about this today. The radius and interval of convergence of power series. I understand you guys are coming in late, missing all the good stuff here. All right. Any questions before we get started? No questions about like the tests, guys. I really hope you're not waiting for whatever reason to practice using these tests. Okay, I've only gotten a couple of you send me examples of like your write-ups, and I appreciate that. It shows me that you guys are listening. But if you want to like do a practice problem and write out your write-up, or write up your write-up, right? And then you send it to me, I will give you feedback on it. I'll be like, oh, make sure you tweak this, make sure you say this, make sure you say that. All right. Because on the quizzes, I'm not going to be like, okay, don't forget to do this, don't forget to do that. Me or China, we're not going to tell you to do that. Your write-ups need to be good. Your justifications need to be sufficient, right? If they're missing something, so it's like integral test, right? You have to have those 3 things. If you don't mention those 3 things, that's points off. AST has to have 2 things, right? If you don't mention those 2 things, that's points off. DCT, there has to be something you compare to. You got to tell me about it. You got to make the comparison, and then you can say your final answer. So work on those write-ups. If you want to meet with me and be like, hey, can you help me with the write-ups? By all means, do it. Right? I'm available. With that being said, let's move on to 10.6, which is power series. I got real excited talking about them last class. Does anyone remember what I said about them, power series?
That they're pretty much a function.
Yeah, like a function.
They're pretty much a function. So it's not that. Yeah. So it's basically going to be a series, right? That has a Actually, I'll use C. I think I used C last time, right? There's like a series part, and then it involves something with an X in it, a variable. Usually from 0 to infinity, but that is whatever. And I said that these power series will represent a function. And notice I'm using the squigglies. If you don't know what the squigglies mean, it means approximate, right? So what this means is it's going to approximate a function. Yeah. And if you think about it, if I string out the first couple of terms or the bunch of terms, right? It's gonna look something like this. It's gonna be like the sequence part. Oh, it's 0. The sequence part, right? Whatever you get when you plug 0 into the sequence, and then I guess this would be 1, right? Because anything to the 0 power is 1, and then this is gonna be plus the first sequence part times x minus a to the 1. And then the second one and so on and so forth. It goes out to infinity, right? And the idea is when you string this out to infinity, okay, this power series is going to be a good representation of a function. And it can be actually any function, right? So I was kind of saying like how this kind of opens up avenues into differential calculus and integral calculus, right? We can derive this stuff and integrate this stuff, right? Like I can derive, it's called term by term differentiation or term by term integration, right? So I can like do whatever I want with these functions that I normally would do in calculus, you know? So we're gonna get to that towards the later half of the lecture, but for the first half of the lecture, I wanna show you guys kind of how to see where this is going to be a good approximation. Okay, so let me claim here, this is only a good approximation on, come on, jump on here, let's go, on the, it's called interval of convergence. Interval of convergence. Can you guys see that? I know it came out a little thin there, I don't know why. Interval of convergence. So we're going to focus on that for the first part of today's lecture, right? So let me pull up an example here because I know you guys don't like it when I get all theoretical on you. So let me jump to the first example here. Okay, so let me just give you a power series and we'll like play with it. Okay, I'm going to call this example. Oh my gosh, what is? I keep doing that. Example 1. This one's actually on page 592 in the textbook. And it's the sum from 1 to infinity, 2 to the n over n factorial. Wait a minute. Oh, sorry. Nope. I am on the wrong section. Sorry. We're on page 598. That was the wrong problem. So n equals 0 to infinity of x to the n over 2 to the n. So once again, anything with an x in it, if you're given a series with an x in it, immediately you should know that this is a power series. Okay? And good news for you guys, to find the interval of convergence, it's really, really easy to find it. You always use the one test. It's actually the ratio test. Okay, so watch. So I'm given this power series, and once again, it represents some function. I don't know what the function is, right? I mean, not now, right? Like I don't know what the function is, but I know that it's going to represent the function for some values, right? So let's try and figure out what those values are by finding the interval of convergence. So we're going to use the ratio test. Okay. We're going to use the ratio test on this like we normally would like with a regular series. How am I doing? Am I going too fast?
No, you're doing good.
All right. So I'm going to use the ratio test on this. So help me out here. I'll get you guys started. Limit as n goes to infinity of what? How do I set this up?
So it's going to be of x to the n plus 1 over
absolute value, x to the n plus 1
yeah. over 2 to the n plus 1.
Good.
And then all that over xn over 2n.
Right. So I kind of did like we can skip that step.
Yeah, just multiply it by.
Yeah. We're just gonna multiply it by the reciprocal because that's the same thing, right? But I appreciate that you said that. So we got 2 to the n over x to the n. So far, so good?
Yeah.
Okay. Let's simplify this thing right here, right? It looks like this is going to cancel out with that. And then this is going to cancel out with that. Leaving me with x over 2 and those absolute value signs. Why can't I just get rid of the limit now?
There's no n.
I think I heard Harry say it. Yes, there's no n. There's no more n's, right? So A very, very common mistake that I see a lot here is people confuse this n for x. Okay, they're two different variables. They are two different variables. So please keep an eye out for that, okay? Don't say that this is infinity. That's wrong. Okay? We're not taking x to go to infinity. We are taking the indexed n value to go to infinity, okay? So let me kind of once again reiterate here. What is x then? If x is an n, then what does x represent in this problem? In this situation?
Yeah.
What?
Would it be the function?
Well, x doesn't represent the function. F of x represents the function, right?
Yeah.
So
what
is
is
that
x?
the output?
Oh,
I mean,
come on, man.
the input?
Yes, the
Sorry.
input. X is your input, right? X is your input, Y is your output, right? Come on, right? So this input, this value, this X here, it represents your input of the function, okay? It represents all the things that can go into the function, any number that you can plug in, right? So this is the input of F. Well, depending on what that X value is that's going to determine the outcome of this ratio test. You guys catch that? Do you see what I said?
Yeah.
Depending on what this X value is, that's going to determine whether or not the series for that one input will converge. So for example, if I plug, let's say X is equal to 1. What would happen? What does that mean? What can we conclude?
That f of 1 is equal to a half?
No, be careful.
The absolute value.
X is equals to 1 and 1/2, and 1/2 is less than 1 in convergence.
So what converges? So okay. So
The
if X is
series
equal to 1,
convergence.
this is less than 1. So which series converges? That was the question.
X to the power of n over 2n.
Remember, it's not X anymore.
1 to the power
Yes.
n
Oh, yeah.
over 2
We're
to the
looking,
power of n.
we're looking at a
Yeah.
very, very specific case here, right? You see that? And of course that
Yeah.
one converges. I didn't have to use ratio test on that. That's a geometric series, isn't it?
Oh yeah.
So what I'm trying to get you guys to see here is that this X, what this X does, it opens up a huge amount of values that, like, it takes on a certain amount of series that this original series can be. Because watch, what would have happened if my X value was like 4?
Could be 2.
Huh?
It'll be over 1 to a divergence.
Exactly.
Yeah.
The ratio test would be a divergent conclusion. So that means when X is 4, right? If X is 4, that one example would diverge, which means it's not a good representation of the function at 4. Do you see what we're doing here, right? So instead of going through all the numbers that X can be, what is going on with Mohammed? Instead of going through all the numbers that X can be, we're going to leave it as X and find a window, find an interval of all converging answers. Because everything outside will be divergent. Does that make sense?
Yeah.
And this is called the interval of convergence. That's what we're looking for. We're looking for where the series represents the function really, really well. How am I doing? Did any of that
Yeah, I
go in
understand. So
It makes
okay, I
sense.
understand.
Makes
It makes
sense.
sense.
Okay. All right, cool. So that was just like my little side point. So let's kind of keep playing with this. We did the ratio test on the general term, and we want to see when that, after you compute the limit, when that is less than 1. Because if it's less than 1, then we get
Convergence.
yes, converging values of X. Yes. So let's do that. Let's solve this inequality, and this is going back to algebra here. I don't know if you guys remember how to solve these absolute value inequalities. Everyone.
Yeah, I remember. You had to put. I actually did this yeah, I reviewed it. It's going to be x over 2 less than 1 and x over 2 greater than -1.
Good. Because there are absolute value bar signs, we have to consider the negative values also. That's the short way to say it. And from here, well, how do I just get x? I just multiply everything by 2 and I get.
Yeah.
Okay. And that's it. This is oh, I lied. That's not it. But this is almost the interval of convergence. I write IOC for short. Okay, if you write IOC, it's fine. But this means interval of convergence. So there's a catch, okay? What this is saying is anything between -2 and 2 will go into the original series, right? Anything that any of those values that you plug in for this x will create a converging series, okay? Which means anything in between those values, you can plug into the series and it will represent the function. Yeah?
Yeah.
And then anything outside, like we said, right? If I plug in 3 or 4, or if I plug in -3 or -4, will create a bad representation of the function. Yes?
Yeah.
Okay. There's a catch. What about at the endpoints, meaning 2 and -2? Can we say that that is also divergent or convergent?
No, because
No.
isn't it if it equals 1, the test is inclusive for ratio test?
Yes. So what do you think that means? Connect the dots. Connect the dots.
That means it's inconclusive on 2
Well,
and
yeah. So Ali's saying if I plug 2 or -2 into there, I get an inconclusive statement with the ratio test. So that means
That it-
that
You got to use another
If-
test.
oh, who said it? Alvaro, my man. Yes.
uh,
Yeah. So what does this mean? This means this is very, very important. You know, I'm actually going to star this and write this in red. Test yo mother freaking endpoints. Okay? This is like an extra step you must. What the heck just happened? Okay, all right. All right. Yeah, there you go. So you must always test your endpoints because of this inconclusiveness that we get with the ratio test. And what does that mean? I'm going to plug 2 into the original problem. I'm going to plug -2 into the original problem and see what happens. Does that make sense?
yeah.
So watch. So I'm gonna do that right here. So test. I'm gonna test x equals 2. All right. So we get come on. So we get 2 to the, help me out here. Is it n? Over
It's x, 2 to the n over 2 to the n.
to the n. And this it's from 0 to infinity.
Yeah.
So do you
1
guys see
to
what
the
I
n.
did? I just replaced the x with 2 because I'm testing 2. And then this is the same thing as 2 over 2 to the n. You're allowed to do that because of exponent rules, right?
Yeah.
Yeah.
This becomes 1 to the n. So I'm left with summing up 1 to the n an infinite amount of times. So what do you think? What is this?
Diverges.
Diverges. How do you know that?
It just doesn't decrease, like diverges in test if I want
There you
to.
go. So those tests, those 8 or so tests that we learned, this is what we're going to use them for. For this specific reason, right? All those tests we have to know very well so that we can apply it to these endpoints and see if this converges or diverges. So we found when you plug in 2, you get a diverging series. So we leave this open. It's just less than 2. It's not less than or equal to 2, right? So after we tested 2, now we got to test -2. Yeah? So we get -2 to the n over 2 to the n. This is the same thing as, I'm just going to use exponent rules again, -1 to the n times 2 to the n over 2 to the n. You see how I did that?
Yeah.
-2 is the same thing as -1 times 2, and then I just broke it up. So it kind of creates an alternator. This cancels out the 2 to the n's, and you're left with I call this the light switch, right? Because it goes positive 1, negative 1, positive 1, negative 1, positive 1, negative 1, positive, negative 1. So what's going to
Binary.
happen? What's going to happen to the
It
sum?
goes to 0.
No, it does not. If I write this out, this becomes 1 plus negative, I'm sorry, 1 minus 1 plus 1 minus 1 plus 1 minus 1. Will that ever settle on an answer?
So when
No,
does
but
it be
it
1?
constantly.
What?
When they just end up converging at 1? Well, no,
Okay,
never mind.
1 minus 1 is 0 plus 1, and then
Never
this is going
mind.
to be plus 0. And then there's going to be like minus 1. Oh, wait. Yeah, so it's going to turn out to be the same thing. Like if something's like flipping between two values,
Oscillating?
I mean, it's oscillating. So does that ever converge? Will that ever settle on one answer?
No.
Yeah.
No.
No.
No, the answer is
No.
no.
So
Okay, so some physicists believe that, I mean, this is just an aside thing, and this is why physicists and mathematicians, we don't like each other. We don't like each other, right? Some physicists believe that this is actually 1/2. There is a proof for it, but it's kind of like a meh kind of proof, you know? It's like mathematicians don't really like that proof, you know? It's like we're like, you know? But for mathematicians around the world, they believe that this is divergent by the divergence test, because it never settles on an answer. So don't say it equals 1/2, all right? Don't be smart. Don't be smart.
If
So
we do,
what do
though, is the minus points.
Yeah.
Come on, man.
So what did we do?
It's zeros.
We tested both ends, and we found that it diverges at both cases. So we can say that the interval of convergence is in fact -2 to 2.
I had a question.
Yes.
For the one where you used -2 as the x value,
Yes.
what if you don't use the divergence test and you use like the geometric test, the geometric series test?
Oh
Because
yeah.
then it would
yeah, totally.
then it would give you 1/2, and then so like
It would not give you 1/2.
oh it wouldn't.
Yeah, this right here. That's your
Yeah, wouldn't that give you 1/2 if you use the geometric series?
your R value is -1, right?
And your A is 1.
Right.
I thought it was 1 over 1 minus negative.
But what does the geometric series say when R is 1 or greater than 1?
I thought it was if R is less than or equal to 1, you can use the sum.
but it's the absolute value of R, no?
Yeah.
Well, okay, fine. The absolute value of R, which is 1. But
Yeah, if it's less than or equal to 1, you do A over 1 minus R.
if I have, guys, think about it. If I have this, right? What this is going to be 1 plus 1 plus 1 plus 1 plus 1 an infinite amount of times. Does that converge or diverge? If this goes to infinity,
Diverges.
that diverges.
Mhm.
So either maybe I told you something wrong, or maybe you guys wrote something down wrong, because the geometric series is only conclusive when it's in between 1 and -1. Because do you guys remember the original geometric series thing? It was like something over like 1 minus R in the bottom. It was like A minus AR to the n or something like that. That was like the first definition of this was the first definition of geometric series. This is what led us to A over 1 minus R, right? And the reason we were able to do that is because we said R has to be in between 1 and -1. Right? I don't know. Maybe I might have said less than or equal to by mistake. But because look, if I can't plug 1 into there, right? If I plug 1 into there, I get infinity, which is a no. Did that help, Philippe?
Yeah, you got it now.
All right, cool.
No
All right.
1/2 here.
So what was I gonna say? I don't know. Why don't we do another one real quick here? I can't remember what I was gonna say. Let's do one where the interval converges and diverges. Okay, so let's look at this.
John,
Yes, sir.
so now that we proved that the endpoints -2 and 2 are included, do we have to also put?
We just proved that they're not included because they diverge at those.
Oh, because they diverge.
Mhm.
Okay.
If they converged, we would have to include them. We would have to do the less than or equal to,
Oh,
right?
okay.
So let me reiterate here. So the interval of convergence is I'm just going to do the shorthand, -2 to 2, that guy. Or you can also write this as x is in between 2 and -2.
So that's all we would like put down for a problem like this?
Yeah, after you write all this work.
After, yeah, you explain.
Sometimes you're going to see something called the radius of convergence. Radius of convergence just means the distance from the center to one of your endpoints. Does that make sense?
Yeah.
Right. So I don't know if I was explicit with this before. With power series, this point right here is called the center. All right. So for this example, our center was 0, wasn't it? Because it's x minus 0 to the n.
Yeah.
Yeah.
So the radius of convergence on this one is going to be 2. Because the distance from 0 to 2 and the distance from 0 to -2, that's 2. Okay, thanks, Shubham. I guess he has to watch the video then when I posted it. All right, so let's try another example here, okay? Once again, I'm given a power series. How do I know that this is a power series?
X.
I see the x, right?
Yeah.
And in fact, you can tell me where the center is too, right? What's the center on this one?
5.
It is 5.
Yeah, 5.
Yes, it's 5. Yep.
Yeah.
All right, so here we go. We're going to do the ratio test. All right, I'm going to go through the ratio test kind of quick here because I want to get to other stuff. All right, so we take the limit as n goes to infinity. Absolute value signs means I can just get rid of the alternator. So what am I left with? X minus 5 to the n over 4 to the n. I'm sorry, n plus 1. 4 to the n plus 1, and then an n plus 1 here. Times the flipped, right? I'm just going to flip everything. So it's going to go x minus 5 is on the bottom to the n, 4 to the n on top, and just an n. Absolute value. We're going to cancel some things out, right? 4 to the n cancels out with 4 to the n plus 1. N and n plus 1, when I take that limit to go to infinity, since they have since they both have the same rate, this is just going to go to 1. And then I'm going to get rid of this x minus 5 and the n plus 1. Leaving me with x minus 5 over 4. Was that too fast? Anyone
No, I got it.
go through any of that again?
The only thing was the ends. You said that. How was that one again?
Because so the thing I did in green, right? I have an n on top and then an n plus 1 on bottom. If I take the limit as that goes to infinity, what happens?
They both go to infinity.
Well,
It's basically 1 over 1.
it ends up being 1 over 1, right? This is the same thing as 1 over 1 plus 1 over n.
Oh yeah.
So it goes to 1. I just didn't show that step.
Gotcha.
Okay. All right. So you do the ratio test. I have this thing without, like, there should be a step where there's no more ends, right? I shouldn't see any ends at this point. Now, I want to find the interval of convergence. So I'm going to set this less than 1 and solve this algebraically, right? So this becomes x minus 5 over 4 is less than 1, greater than -1. We're going to do some algebra here. Hopefully this is the easy part. Multiply everything by 4. Add everything by 5. Questions? Comments? Concerns? John, how did you get that 1? How did you get that -1? Where did the 4 go? No? None of that? Okay. So we found our possible interval of convergence, right? This is not the interval of convergence yet. We haven't proven it yet. What do we have to do? I wrote it in red
Yeah.
before.
The endpoint.
That's
Yeah,
the
test-
over the
Test your freaking endpoints. If you forget to test your endpoints on the quiz or whatever, I'm going to take off 100 points. Okay? I don't even care that the quiz is going to be like out of like 30 points. I'm going to put you in the negatives. Okay? Please make sure you test your endpoints. It's very, very
Yeah,
important. Right?
we were talking about that yesterday. Talking about negative grades, teachers giving negative grades.
No, that doesn't.
It
Matter.
says it's a 91, but it's actually when the negative grades come in.
I mean, you know, a curve is a curve, right? So, okay.
Yo,
So we're gonna
finna
test
cut the
x equals 1. So, man, so when we test it, we have to plug it into our original series, okay? Which means we got to include the alternator now. All right, so keep that in mind. So help me out here. What is this going to become? Because I don't remember what it is. I know there's an alternator. Is it like that?
Yeah.
And then
Over 4 to the power of n times 1 minus 5, which is negative 4 to the power of
1
n.
minus 5 to the, like that?
Yeah, but yeah,
Is it from 0 to infinity?
from 1 to
Yeah.
infinity.
Oh, it's
Oh,
from
no,
1
yeah,
to
1
infinity.
day.
Okay. Everything else is good?
Yeah,
The negative 1 is to the n, right? Not to like the n minus 1 or something?
yeah.
Okay. So I'm going to test x equals 1. All right, I'm going to simplify this. This becomes negative 1 to the n times negative 4 to the n, over 4 to the n times n. So we got to clean this up a little bit. This becomes negative 1 to the n times another negative 1 to the n times 4 to the n over 4 to the n times n. Why did I do that?
So you can cancel out the 4 to the n.
Good. So I can cancel out the 4 to the n's, and what else is going to happen? What can I do with these negative 1 to the n's?
Combine them.
Right. So what
Yeah,
does that
turn it
do?
to positive 1. Yeah.
Why? Why does it become positive 1?
Two negatives.
You have the same
positive.
exponent.
It's not, okay, so remember, we're still using exponent rules here, okay? We're not doing negative 1 times negative 1. We're doing negative 1 to the n times negative 1 to the n, which gets us negative 1 to the 2n, which is the same thing
And
as
then negative 1
negative 1
squared.
squared times
Yeah.
1 to the n. Does that, so that should explain why the negatives will cancel out, right?
Mhm.
Okay, so what am I left with? Oh my gosh, what is that? Oh shoot, sorry.
1 over n. It
And
always goes back to 1 over n.
not always.
Yeah, I know, but yeah, I'm talking about examples.
What do we know? What do we know? What do we know? Come on.
That's a harmonic series.
Harmonic
That
series.
diverges.
Sum of 1 over n diverges. So we do not include 1 in our final answer. It's going to stay open.
So you can just say diverges by,
Sorry,
because
I forgot to
harmonic
say why.
series.
By harmonic series, yep.
So-
Like I said, harmonic series is a very well-known one, so it's like you don't have to say P series or like do the integral test or something. All right, so we tested the first endpoint. Let's test the second one. The second one, which is 9. So we get
Yeah.
from 1 to infinity. This becomes negative 1 to the n, 9 minus 5 to the n over 4 to the n times n. Sorry, this thing's like lagging a lot. It's because there's so many notes on here. This is the same thing as negative 1 to the n, 4 to the n over 4 to the n times n. Anyone see it? Anyone see it?
Yeah. Amazing. I honestly mean that.
Does that look familiar?
Mhm.
1 over n with an alternator.
So
Oh, doesn't it? Isn't this? Oh, hold on.
come on. Once you see an alternator, what test do we use?
AST.
Alternating series.
Alternating series
Alternating
test,
series test.
right? Okay, you guys have not been practicing, huh? I know it's only been a couple days. I just have high expectations for you guys. You know, I really hope you guys know that. I have very high expectations for you guys.
Thank you.
Okay, that's it. All right. So this is decreasing and goes to 0, so converges by AST. Yeah, don't worry about it, Mohammed. Just rewatch the video like in your own time, okay? So what did we just say? One endpoint diverges, the other one converges. So
We include one.
say the
So,
integral
yeah.
of convergence
It's
is
from 1 to 1, yeah, equals to, less or equal to
that's
9.
not 1. Where are you getting 1 from?
Yeah, it is 1.
It is 1?
Yeah.
Yeah, the
Oh,
test
I'm
was at
sorry.
one.
I'm sorry. I was testing you. 1 to 9.
Yeah, less or equal.
Now we have to include 9. There you go.
We could put it in interval notation, correct?
Yes, interval notation is fine too. So if you do 1 comma 9 and bracket.
John, one quick question. With AST, when we do like when we say that it's decreasing, do we prove that it's decreasing?
No, not for me.
right, I
I
got
don't
you.
think professors really care if you. It's just one of those like it's very obvious if they're decreasing, you know. So like I don't need to prove it. I know we just learned this, but anyone want to tell me what the radius of convergence is?
And the radius of convergence is 5.
That's the radius, but that's not
Not
the
5.
distance.
Radius of convergence. Once again, it's the distance from the center to the endpoint.
Center to that point.
Our center
Yeah.
is
Also, the R2
5,
4.
so 4.
yeah.
Oh,
which is
yeah,
4.
4. Ah, I'm an idiot.
The distance
that-
from 5 to 9 and 5 to 1 is
Yeah.
So the radius of convergence is not dependent on the endpoints being divergent or convergent. It doesn't change.
yeah, no, because radius of convergence is like it's a distance, right? So it's like think of it like a radius of a circle, right? Like from the center to anywhere on the outside of the circle. It's like the same idea.
Okay.
Okay, thank you.
Okay, can you explain why it's 4?
So remember what I said in the beginning? The center was
It's 5. The center was 5.
5.
So from 5 to 9 is only 4.
So the radius of convergence, what the heck? The radius of convergence is the distance from 5 to 9 and 5 to
And
1.
okay.
John, could you always just do the like 9 minus 1 divided by 2?
You can do that too, sure.
Oh, okay, that works too.
Right? That's the midpoint, right? How to find the midpoint of anything. So it's like you just subtract and divide by 2. That's another way to do it. How is this? Is this okay? This is pretty much all of power
Yeah.
series.
Yeah, this is good.
So
Yeah.
given any power series, now you should be able to find the interval of convergence and the radius of convergence, right?
Yeah.
Okay. I'm going to do, oh man, I wanted to get to this. All right. I'm going to show you 2 other cases, but I'm going to kind of do them kind of quick. All right. Okay. So with power series, there are actually 3 outcomes that you can get with power series regarding the interval of convergence. Okay. It's on page, it's theorem 1 on page 597. So theorem 1 on page 597, the PDF number. There are 3, and they write it all in words, but there are basically 3 outcomes that you can get. 3 outcomes with the interval of convergence. There are 3 outcomes that you can get with the interval of convergence. The first outcome is what we just did, right? It's going to be x minus c. They write it like this, where r is your radius of convergence, and x minus c is the like, you know, the x minus the center, right? So so what this is trying to say is convergent on an interval, right? Convergent on a specific like interval. It's x is less than r plus c, and then like negative r plus c. This is what we just did. This is, and then like, you know, you got to test endpoints, right? This is just like the generalized notation for it, right? So we would test one endpoint, test the other endpoint, and get a final answer. So that's the first case. The second case is that it only converges at x equals c. Oh, I'm sorry. I used a, didn't I?
Yeah.
Let me be
for-
consistent here because I don't want to screw you guys up here. I think I used A as the center, so I'm gonna change it to A. I think the book uses C. Dang, I screwed that up again. So what does that mean? Converges only at one point.
At the center.
It only converges at the center, meaning the sequence part, right? The sequence part, it diverges. And the only way to kill a diverging thing, right, is to multiply it by zeros. I'm going to show you an example of that in a second, okay? I know that didn't make any sense. And then the last case is converges everywhere. Everywhere, right? So it's x is in between infinity and negative infinity.
Oh, that's probably when we can't remove n.
Yes, yes. It's sort of. It's when you get to the ratio test part and your conclusion ends up being 0, regardless of what x is. I'm going to show you an example. These examples are going to be quick, all right? But for the most part, like you're probably going to come across the first case. So let me do another example. What I guess that was like example 1, so I'll call this example 2. Where is this? Okay, ready? So here we go. The sum from x to the 2n over. Oh, this one's a special one. Okay, so watch. Without even just doing this problem, okay? So 1, it's a power series, right? Because there's an x in it. But without even doing the ratio test, can you guys just look at this and tell me like what you think is going to happen? Like just look at the bottom, look at the top. Like what do you think is going to happen here? Okay.
Wait.
Is it that?
So okay, maybe if I rewrote it like this.
Is the top growing faster than the bottom?
Don't forget what is x, what is n? You know which is which? You know, like what do they represent?
Would it converge?
What, Philippe?
Would it converge?
Converge. Give me a little bit more.
Converge to the center. Dang, I got that.
Okay.
Okay,
Look,
wait.
just think about it. Look, x is our input, right? That means x is going to be like 1 or 5 or 7 or a number, right? Within our domain. But this 2n factorial on the bottom, it is just going to keep on growing, regardless of what the x is, right? The 2 times n factorial is going to keep on growing and growing and growing and growing really, really fast, so fast that the x will not be able to keep up. So the question then becomes, does it matter what I put in for x?
No.
No.
So this is going to be the case where this converges everywhere. Does that make sense? Meaning I can plug in any value of x and it will be a good representation. It will always be converging because the bottom just grows way too fast. So let's prove it using the ratio test.
Is this like using the knowledge of like the growth factors, or is it kind of just
okay. It's kind of like I'm trying to get you guys to build your intuition when it comes to these problems. Like, you know, you should be given a problem now and you should be able to think it through and be like, I think this one's going to converge, I think this is going to diverge, or I think the interval is going to be blah blah blah, you know, like, so I'm trying to help build that intuition in you guys. All right, so this becomes 2n plus 1
n factorial
times 2n factorial over x to the 2n. Please watch out. Very, very common mistake. People forget to distribute when in these cases. All right, so people tend to forget to distribute. They would write this as 2n plus 1 factorial, which is wrong, right? This should be 2n plus 2 quantity factorial, right? Same thing with this one. They write it as x to the 2n plus 1 when it's supposed to be x to the 2n plus 2. So what's going to happen? What are we left with here? I see that this x to the 2n is going to just get rid of that one. So I'm left with an x squared on top. And then I'm going to write this out for you guys, right? 2n minus 1, 2n minus 2.
Well, yeah, China showed us that. No, so that I remember the tricks you showed us with n plus 1 factorial equals n plus 1 times n factorial.
Yeah, John, can you
Yeah,
just take
whatever.
out the 2?
Yeah, take out the 2 and
Then you would just have n factorial and then n plus 1 factorial.
No. So it doesn't work like that.
Mhm.
Yeah. The factorial doesn't like distribute like that.
So you have to, okay, so you can't
Yeah,
take it
so like 2 factorial n factorial does not equal 2 n factorial. Factorials are weird. You mainly play with them in like probability and statistics pretty much, but they come up here too. So just like don't get duped by that. Factorials have different rules. All right, so I wrote everything out and I see that this starts canceling out here, right? So I'm left with that guy on the bottom. I don't know why that came out red. And we're still here. We still need the limit sign because there are still n's in there, right? And this is what I was saying. Even though we simplified on the ratio test step, we still have n's on the bottom that we have to play with. So what's going to happen to this guy regardless of what x is? What is this going to equal?
it's gonna approach 0.
It's going to approach 0. I can plug in 1 for x. I can plug in 6 for x. I can plug in 100 million billion for x. But that will not keep up with this, the denominator growing infinity to infinity. Does that make sense?
Yeah.
Yeah.
So because we came to this case, it doesn't matter what x is. We can say the interval of convergence is x is in between infinity and negative infinity. And that's it. I guess, and you can say the radius of convergence is infinity. It's ugly infinities. I know, I'm sorry. Questions? No?
Answer is
This was it converges, correct, John?
What convergence?
Because 0 is less than 1.
Wait, what?
Like, you know how we got that? Like, you know how it's rho equals limit as n approaches infinity, and then it's x squared over the bottom?
Yeah.
So that would mean that since rho is less than 1, it would converge?
So it's rho is less than 1 irregardless of what x is.
Yeah.
Right? Because it's a power series. If the
Gotcha.
x wasn't there, then you can say that then the problem would just be 1 over 2n factorial. Like this would be the original.
Yeah, I got you.
Right. So I'm gonna leave this example up to you guys to do just because we're short on time. But this is the third case. All right. It's a very easy third case. Do the ratio test on this, and you're gonna see that no matter what you plug in for x, you're always gonna get something divergent, right? Except for when you plug in 0. Because think about it, if I plug in 0 into this thing, it's gonna act like almost like a self-destruct button, you know? The n factorial is growing way too fast, right? So that means when x is 0, it'll cancel out all the terms, and then it'll just be summing up a whole bunch of zeros, which is convergent, isn't it? So you can do this one on your own, left to the reader, all right? But yes, this should be the third case. This converges only at x equals 0. If it was like, I don't know if I tweaked it, if it was like x plus 4, right? Then this would only converge at -4, right? Because that's what would make that value 0.
Yeah.
Okay, so I'll leave that one up to you guys to do. Okay, cool. We got time to do this now. So, how you guys doing with the power series stuff? Is it okay?
Yeah.
Yeah.
For the most part, it should be fine because it involves the ratio test.
Ratio test, yeah.
And everyone loves the ratio test. It's really easy, right? So let me kind of show you guys what all this is kind of for. All right. Let me start with this. So you noticed that I'm not giving you the function, right? I'm just giving you a series, and we're like, it represents a function. So it's like, I could actually just be lying to you this whole time, and you guys wouldn't even know. But I'm not. Don't worry, I'm not. I promise you, I'm not.
Did somebody ever do that?
I get fired.
Like,
I'll get
would
fired
be
for
awful.
that. Okay. So watch. This is what we're gonna do. We're gonna go the other way now. We're gonna try and formulate a function and turn it into a series that we know, so that we can kind of like visually see what's going on with whole interval convergence and stuff like that. Sound good?
Yeah.
Yep.
Okay, cool. So I'm just for time's sake, I'm just gonna tell you. So do you guys remember? You guys remember this, right? Well, you have to for your next quiz, right? Where does this come from?
Geometric series.
Yeah.
Geometric series, right? So that means it's gonna look like AR to the n equals 0 to infinity, right? And this is equal to A plus AR squared plus AR cubed, and so on and so forth. Still with me?
Yeah.
Well, you should be. This is we did this already. All right, so I'm gonna tweak this so slightly. Okay, we're playing with power series, so I want to turn this into a power series. If you think about it, R is technically a variable, isn't it? R is a variable that falls anywhere in between -1 and 1. So long as this is, that's what makes this convergent. You see what I'm saying?
Yeah.
So what I'm going to do here is I'm going to let R equals X, and then I'm going to let A equal 1, because I want to look at a very simple case. So what does that give me? That gives me 1 over 1 minus X. So that means the only thing that changes in our series is that. You guys see that?
Yeah.
All I did was I substituted R for X and A for 1. And what happened? Well, it's saying that this function, 1 over 1 minus X, is well represented by this series X to the n from 0 to infinity.
Mm-hmm.
Still with me? Still with me?
Yeah.
So I know this is still kind of, oh, I forgot to say and we actually know the interval of convergence, right? Because we actually kind of said it today too, right? We can say from -1 to 1, not including, this is the interval of convergence.
Mm-hmm.
Any disagreements on that? Or like, John, how did you get that?
No.
No? If you don't believe me, do the ratio test on this. Do the ratio test on this. You're going to see that it's X, absolute value of X less than 1. Test the endpoints. It's not going to work, right? So watch, all right? Ready? This is where everything's going to come together, and you guys hopefully will be like, oh my gosh, this is so cool. All right, ready? Let me switch over.
Drum roll.
Don't drum roll. Don't build it up. Let me switch to this.
Yeah, I wish I had my drumsticks here.
Okay, so you guys hopefully know what 1 over 1 minus X looks like, right? This is 1 over 1 minus X. It looks like 1 over X, but then like it's flipped about the X axis and it's shifted to the right. Yeah, right 1. So you guys know what 1 over 1 minus X looks like, right?
Yeah.
Yeah.
It's a parent function. So watch what happens. Okay, underneath, I have a string of terms, right? This is going to be n equals 1. This is when n equals 2, n equals 4. No, wait. N equals 4, and then n equals, can go up to 11. Okay? I want you guys to see what's going on. You ready? This is the cool part. Ready?
Yeah.
Okay, so here we go. 1 plus X. Ready?
Whoa.
Okay, no, not yet.
Okay.
Don't ruin it, man. Come on, man. Gosh. All right, so that's 1 plus X, and you're like, look, what? Anything you guys notice?
It's like tangent.
It's tangent.
It looks
tangent.
tangent,
Slope.
right? It's like touching, like over there, right? Okay, all right. Let's see what happens when I do this. So all I did was I added another term. What do you guys notice?
That
So it's-
one
so
plus
part of the-
X. Yeah.
Part of the parent is like part of the Next term.
They're okay. It's still touching though, right? Like it's
So,
touching
like,
on.
still
like a-
touching. Yeah,
Okay. Let me
they're
go
all
out
still
to.
intersecting.
Let me go out to 5 terms.
Still touching.
It's getting
Oh.
closer to the parent
Ooh.
function.
Ooh, who said it? Harry, was that Harry?
So
Yeah,
Harry, say that one more time.
that as you increase the sequence, it's getting closer to the parent function.
It's getting closer to the function. This is what I've been saying from day one with power series, right? The series will be a good representation of the function on what?
on the interval
On
convergence,
On the interval convergence. What did we say the interval convergence was?
1 and negative
From
1.
negative
Negative
1
1
to
to
1.
1.
Do you
And
see
then
that?
it, yeah.
Do you see how from negative 1 to 1,
Oh.
this polynomial is a pretty good approximation of the actual function. But look, I only went out to 5 terms. What would happen if I go out to more? Let's see. This is 12 terms.
Whoa.
You see that?
Whoa.
You see that? You see how it's like almost like on top of each other from negative 1 to 1?
Yeah.
Yeah? Pretty cool,
Yeah.
right?
What?
Yeah.
Yeah.
I know. It's so
Wait, John,
cool. Yes.
what about the bottom half of the?
Yeah. It like.
Oh, so like, okay, so this part right here.
No, zoom out. I meant like the part that's below the x-axis.
Oh, because that's
Well,
over 1.
Yes, right?
So it has
This
an
is
asymptote.
only good from negative 1 to 1, right?
Oh,
And you see that
okay.
as it gets closer and closer to like negative 1, it like spins off, right? It diverges out to negative infinity or positive infinity because this series diverges out.
That's
Oh my gosh!
crazy.
Yeah, I know. So this is, like I said, this is only for 12 terms. What would happen if I went out to 100 terms, to 1,000
Close to
terms,
it.
to a million
It's gonna
terms?
get
I don't have that
closer.
time. I don't have that time to type all that in. You would see that it gets closer and closer to negative 1, but then at negative 1 and 1, it's not a good approximation, right? You see that? Oh, people talking in the chat. Don't be shy.
Oh, Rachel. She said that.
Oh my gosh! Oh, I'm so touched. Okay. Oh, sorry, I won't cry. All right. So that's what I wanted to show you guys. All right. The application part of these series. Okay, and hopefully you guys can see, right? You ever wonder in your calculators, right? How does your calculator know, like sine of 3 or sine of 10 or cosine of 100, or how do you think your calculators know how to do that? Do you think a programmer was like, okay, when the input is sine of 1, output this. When the input is sine of 1.5, do this. That's too much, right? That's way too much. Calculators use series to calculate this stuff. So in fact, that long string of decimals, right? So if I have a ROM thing of the 83. So like, you guys can see that, right?
Yeah.
Okay. So if I punch in sine of 8, like the calculator spits all this out by using series. It uses the series representation of sine to spit out all that, because that's easier than like when the input is sine of 8, you know what I mean? So that you can actually input anything you want and it'll spit something out. You see what I'm saying? So this is one of the huge applications of series. It helps with computer like science and like coding and all that kind of stuff. Right? So yeah. Let me. Is there time? There's like 2 minutes. Let me try to squeeze this in, please. So I'm gonna. Oh my gosh! Did I just exit out of the Zoom meeting? Oh, thank God. All right. So I'm gonna show you guys what I'm talking about here. So we said 1 over 1 minus x is this on this interval, right? I just showed that to you graphically.
Mm-hmm.
And what this, come on, oh my gosh. What this means is now I can come up with another function. If I came up with a function that resembled this, 1 over 1 minus x, I could turn it into a series. If I had 5 over 2 minus 3x.
Mm-hmm.
This one's a little trickier, but if I had something like that, this is the same thing as 5 times 1 over 1 minus 3x. Do you see what I did there?
Yeah.
I basically rewrote it to look like the 1 over 1 minus x thing, right? So this means like I can kind of like say that this whole thing is that x value, right? So what does this become? This is going to become 5 times the sum from 0 to infinity of
1 minus 3x to the power
1 minus
n.
3x quantity to the n. And I can figure out my interval of convergence using the ratio test, testing the endpoints, everything that we just did. You guys see that?
Who needs fractions anymore? Like
We all know fractions, right?
it's manually do decimals for all your problems.
So you would do the ratio test on this, ratio test, find the interval, and yada, 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 right?
Yeah.
And then, so I'm going to leave you on this cliffhanger, okay? What happens now if it doesn't look like 1 over 1 minus x? If it doesn't look geometric? For example, what happens now if I'm given something like sine of x? Don't you want to know what that looks like as a series? I do, right?
Yeah.
We're going to talk about this next class, how to turn any function into a series. And that's where Maclaurin and Taylor series are going to come into play. All right? Sound good?
Mm-hmm.
All right,
Yeah.
so that's it for today. Get practice in with those tests. Get practice in with power series, okay? If you want, like I said, we're in section, I'm using the wrong mouse. We're in section 10.6. So I would say look on page, ooh, there's a lot here. Page 605. So page 605. This is probably where your homework's gonna come from. Numbers like 9 to like, oh my gosh, 34 are all great examples of power series. You can do the ratio test on them, test the endpoints, get some good practice, all right? And like I said, your homework's probably gonna come from here. All right, so that's it for power series. Next class, we're gonna do Maclaurin-Taylor. The one after that is gonna be more Maclaurin-Taylor and review, and then Thursday is your final. Oh man, I'm gonna miss you guys. Oh, I know. I won't say this yet.
Yeah, no.
I'll save it for Wednesday and Thursday. Okay. All right. But if you guys have questions, feel free to stick around. If not, I'll see you guys on Monday.
Later, John. Have a good one.
See you.
Bye, John.
Bye bye.
See you, John.
Thanks, John. See you.
See you.